In the previous lecture, towards the end of it, we were discussing the procedure of converting a continuous signal or a continuous function, that is to say, a quantity that is a continuous function of time, into something that is discontinuous. So therein we discussed the process of sampling, and we sort of said that we will take snapshots of the signal at certain time intervals, at certain regular time intervals, and we will just note down their values. So what we saw was that at regular intervals, that is decided by the sampling rate or the sampling time Ts, we saw that at time t equal to 0, the voltage is 0. At Ts, it's 2 volts. At 2Ts, it's 3 volts, and so on. So, if we were to sort of write this signal, which is now a discrete time signal because we have taken the values at discontinuous points. So if we write that the time and let's say the voltage, let's say time t equal to 0, the voltage is 0. At time Ts, we saw that the voltage is 2 volts. At time t equal to 2Ts, it's 3 volts. At 3Ts, it's 5 volts. 4Ts, it's 7 volts, and so on. Suppose we were to denote the signal in this kind of a format. So now what has happened is that the signal has become a discrete time signal. That is to say, its values now exist at certain points in time only, and at all other values of time, the signal is considered to be 0 or non-existent. So therefore what we now have is that we have these voltage values which are distinct and finite in number. So therefore the question of having to store these signals or to store the voltage values of these signals, that sort of gets addressed, because since we have finite number of points, we can store finite number of points more easily. But the next question is that in what manner do we store them? In what manner do we store them? We have something that is 0, we have something that is 2, 3, 5, and so on. One way to store voltages would be to simply charge a capacitor by feeding it a voltage that is equal to the voltage with which we would like to store. However, that's not always a very reliable thing to do, because sometimes the capacitor might discharge through means that we are unaware of. So therefore, that capacitor technique is not always a very reliable technique, although it is used in many places still. The other question is that while we have converted the signal which was earlier continuous into a discrete time signal, that is, we have bounded its existence in the time domain, but in the voltage domain there is no such restriction so far. For the sake of simplicity, I have shown you that the voltage can take any value. In this case, I've shown it to be some integers. It could be decimal numbers also. It could be fractions. The point is that these voltages are still continuous values. So therefore, before commenting any further, we have to know that yes, the voltage can take any value. So there is no point in trying to discretize anything in the voltage axis. So rather than trying to limit things over there, because if we try to discretize something on the voltage axis, we might lose some of the information, that is the voltage value that we are actually recording might be something different than the actual voltage, so which may cause that the signal that we are actually converting into discrete time could be little different from what is its continuous value. Therefore, what I mean to say is that there could be some error. So rather than trying to discretize things in the voltage domain, the way to represent them and then also store them, let us not forget what we are trying to do. We have to ultimately store these voltages somewhere or represent them in certain manner in which it is convenient. So therefore, the next question is that whatever be the voltage value, whether it is an integer, whether it is a floating number, can these voltages be represented in a certain way by using fixed or known voltages? Can these voltage values be represented using a set of fixed or known voltages? Now, when I say a set, it could mean a number of voltages. But let us not forget what we are trying to achieve. We are trying to correlate digital and logic. We had said that in the previous lecture, we had discussed that logic is the way in which we take decisions. So therefore, to take the decisions, there are a number of parameters which we need to consider. And if those parameters can be represented using a set of yes and no's, that is something that helps us take a decision. So yes and no, what we had said, we can assign them some voltage. Let us say yes is a high voltage, no is a low voltage. So essentially the set of voltages that we are talking about could have two values, a high voltage and a low voltage. This also makes some sense because in most electronic circuits, we have two voltages. Or rather to speak, we have two DC voltages which are used as power supplies. One is called as a VCC, the other is called as a ground. Whether you design an amplifier, whether you design any circuit, in DC bias there is always exists two voltages, a high voltage and a low voltage for biasing. So the question is that without losing track of the discussion that we are trying to focus on, can we represent these voltages using a set of known voltages? So let us say we choose two voltages. A high voltage and a low voltage. Now, if we try to represent them in numbers, it could be, low could be 0 volts, low could be minus 10 volts, high could be 5 volts, it could be plus 15 volts. There are many choices available. Now, at this point of time, what is the high voltage value and what is the low voltage value is not of importance to me at this point of time. As an electronics engineer, We can come back to it later on. The point is that we are working with these numbers and we can also assign some numbers to these voltages. So let us say I assign the number 1 to this high voltage and I assign a number 0 to this low voltage. Note that 1 and 0 do not mean 1 volt and 0 volt. That is, there is no guarantee like that. 1 could be 5 volt, 0 could be minus 5 volts, anything is possible. Right? What I am merely doing is that I am representing numerically the high voltage as a 1 and the low voltage as a 0. So therefore, what I am going to do, I am going to represent these voltages that I want to represent using only ones and zeros. So there are two choices that we have. There are two choices that we have. Now suppose I want to represent this 7 volts and I have two choices of voltages that we can have. So therefore, what I will do, I will essentially divide continuously this number 7 by 2 until I get 0 as the quotient. So 2 times 3 is 6 and the remainder is 1. Then again I will divide by 2 because the quotient is not yet 0. So 2 ones are 2 and the remainder is 1. Finally, I will now divide by 2 because I will get the quotient as 0 and the remainder of 1. So what I am essentially doing, starting from the last quotient, I will move over to all the remainders from here all the way till up, and I will write this what I have got: 0 1 1 1 0 1 1 1. So I am noting it all the way from bottom to top. Now this is called as a binary representation. This is called as a binary representation. What I have essentially done is that I have represented 7 using only zeros and ones. It is called a binary because it is a number system with a base of 2, whose basis digits are 1 and 0. You are already familiar with the decimal number system that we use in our daily life, where the basis digits are from 0 to 9. Now, we can do this for 7. We have done this for 7. We can do this for 5 also. Just to quickly show you how it's done, I will divide 5 by 2 continuously until I get a 0 quotient. So 2 2s are 4 and a remainder of 1. Then again I will divide 2 1s are 2 with a remainder of 0. Then again I will divide by 2, quotient of 0, remainder of 1. So again I will represent this all the way from bottom to top. So representation of this will be 0 1 0 1. So while 7 in binary looks like 0 1 1, 5 in binary looks like 0 1 0 1. Now suppose I have this. I have these binary representations. So what? Our original question was, can voltage values be represented using a set of fixed or known voltages? Yes. Now that I have these binary representations, I have these binary equivalents for these different numbers, I can assign some voltage value to 0 and some voltage value as 1. Okay, so suppose I say that I am assigning 1 as 5 volts and assign 0 as 0 volts or ground. You are free to represent them with any set of voltages. As an example, I am showing you this. And the example why I am showing you this, there's a reason for this because it is extensively used also. But in general, there is nothing that binds you from assigning different voltage levels. You can also assign 0 volts as 1, 5 volts as 0. Nothing stops you. Just that it will be a different kind of representation. This is more intuitive. So therefore what we know is that 7, the representation is 0, 1, 1, 1. So therefore this 0 will correspond to 0 volts, this one will correspond to 5 volts, this one will correspond to 5 volts, and this last one will also correspond to 5 volts. That's all there is. So therefore what I can do is that the circuit through which I can represent this would become very simple. So I can say that the first 0 can be represented as a voltage source of 0 volts. The next 5 volts, all I need to do is have a 5 volt battery, DC 5 volts. The next 5 volts would look like this. Another DC source, and the last 5 volt could look like this. So over here, if I bring a voltmeter, I would see a 0, and at all these 3 points I would see 5, 5 and 5. So therefore now you could actually connect them to any circuit that you want. If you connect a resistor over here, you will see 5 volts across this resistor. You connect another resistor over here, you will see 5 volts over here. So essentially, the voltages across the resistors will tell you whether it is logic 1 or logic 0. Because now I am using the word logic 1 and logic 0 because we are again trying to correlate them with yes and no's. Once again, you can assign logic 1 as no and logic 0 as yes. Nothing stops you. I am using this because it is a more well-known and more intuitive manner. So, you will recall that in the previous lecture, we had essentially in the initial part taken an example of making decision using logic. We had said that a child or a student would be given some particular prize by his parents if 2 conditions are satisfied. So, since both conditions were to be satisfied for the child to get the prize, that was called as AND logic. So with that, now let us look at the different kinds of logic functions. The first is called as the AND logic. So let us say I have 2 input conditions A and B, and I have the decision output Y. So very quickly, let us write it down what we had seen in the previous lecture. If both conditions are not satisfied, the decision is also no. So here also, since both conditions are not satisfied, the output will still be no. Only when both are yes, the output would be yes. So now what we will do, we will assign no as logic 0 and yes as logic 1. So therefore, if I now replace this table with numeric equivalents, what I will get is this. Right? This is how we represent the AND logic. So we can represent this AND logic in a circuit form also. It looks like this. This is called as the AND logic gate. But the inputs are the two A and B, and the output is Y. This table where we are showing the relationship between the output Y and the inputs A and B is called as a truth table. Because it represents the truthfulness of this logic making process. So when we are taking the logic decision in our heads, effectively in the electronic format, this can be represented using this notation. This has a deeper meaning also. You may ask, what is inside this AND logic gate actually in terms of circuits? Well, there are things also which we shall see, but for the time being, this is what we are going to stop at. One way to represent the logic function is using a truth table. The other way to represent is using this diagram, what is called as a logic gate. And the third way to represent the logic function is using an equation, where if you notice mathematically, this output Y looks very similar to multiplication, because 0 into 0 is 0, 0 into 1 is still 0, 1 into 0 is 0, 1 into 1 is 1. So since this output Y looks very similar to multiplication of these two numbers or these two inputs, this AND logic is represented using A dot B. This is a representation using an equation. So here we have seen the AND logic, which we had already discussed briefly in the previous lecture. Now let us look at another logic function. This other logic function is called OR logic. Picture the same scenario which we had taken in the case of the AND logic, where the parents would have to make a decision on whether or not the child deserves the prize. Of course, in the case of AND logic, we saw that for the child to get the prize, he would have to satisfy both the conditions. That is, to do well in school as well as clean his room every day. If both of these conditions are satisfied, he would win the prize. But suppose the parents decide to become more chill, so to speak. If the parents decide to become more chill, they say, okay, if the child satisfies any one of the conditions, we will still give him the prize. That is, either he has to do well in school or he has to clean his room every day. As long as any of these conditions are satisfied, we are happy and we will give him the prize. So then in that case, what would the truth table look like? If A is doing well in school, B is cleaning the room, and Y is he gets the prize. If none of them are satisfied, then the child will not get the prize. If he does not do well in school but cleans his room as per his parents' decision, they have to give him the prize. If he does well in school but he keeps his room dirty, that's still fine. He will still get the prize. But if he is a very good student, he satisfies both the conditions, that is still satisfying the parent's requirement of completing at least one condition, so therefore he would still get the prize. This is called as OR logic. Now, pictorially, in terms of circuit, the OR logic is also represented in the form of a gate where the two inputs are there and the gate looks like this. So we can also write the relationship between y and the inputs in the form of an equation. And the equation is a plus b. But, please keep in mind that this is not addition. This is not addition in the arithmetic sense. It just looks like plus. Okay. So, I'm going to put a sign of a danger symbol over here. This is not addition. It looks like 1, yes, because you may say 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, but 1 plus 1 is not 1. Okay, in addition sense. This is called ORing, OR operation. And this is called as the OR logic gate. Okay. Now, we have looked at two logics. One is called the AND logic, the other is called as the OR logic. Let us take a look at another form of logic, which is slightly different from this AND and OR. And that is called as the NOT logic. Now, NOT logic is something that can be understood best again with an example. Suppose I say that I would like to go and watch a movie in the theater. I would like to go to the theater and watch a movie. That is the decision I have to take, whether I should go to the theater or not. Now, to do this, to take this decision, there are two things I have to look at. The first thing is that I should complete my homework by 6 p.m. Or rather, I should complete my homework before the movie. The second thing is that outside it should not be raining. It should be dry. So therefore, let us say my decision Y is, will I go for the movie? That's the decision I have to take. Now the inputs are two, A and B, where A is homework finished and B is it raining? So these are some things I have to look at. So if I now try to write the truth table for this particular example. I will say A, B and Y. A is the homework finished and B is it raining? So here my homework is not finished. Here B equal to 0 means, so let's assign that. So is homework finished? 1 means yes and 0 means no. Here also 1 means yes and 0 means no. So even though it's not raining, I have not finished my homework, so I cannot go for the movie because I would like both conditions to be satisfied. Here my homework is not finished and here it is raining, so all the more better, I will not go. Here I have finished my homework but it is not raining, so what it means, I can go for the movie. Here I have finished my homework but it's raining, so I cannot go. So therefore, in some sense, this looks very similar to an AND logic because somewhere both conditions have to be in agreement, but not exactly. What you see is that if both conditions had to agree or if both conditions had to satisfy, in terms of an AND logic, the 1 would have been here and the 0 would have been here. Now, if I redefine my variable slightly, now if I say A is still is homework done. Is homework done? And B, I will define B in a slightly different way. Earlier B was, is it raining? But if I now say that rather than looking for is it raining, which is not a favorable condition for the movie, I will look for the favorable condition. Is it not raining? Because here not is very important. 1 means yes, it is dry, and 0 means no, it is wet outside. So therefore, with this, if I redraw the truth table, this is what it will look like. Okay, so is homework done? No, so definitely I am not going for the movie. Here also homework is not done, so I cannot go for the movie. Here the homework is done, but B is 0. What it means? Here B0 means it is wet outside. So it is not a favorable condition. I cannot go. Here I have completed the homework and it is indeed not raining, which means it is dry. So therefore this is 1 at the output, which means that I can actually go for the movie. But now what you notice is that the B in this case and B in this case are not the same. They are not the same. So then what is the relationship between these two? If I want to correlate, I will say this B is the opposite of this B, right? This B is the opposite of this B. So therefore, what I say is that the B which I have, if I am reversing its condition, I call it as not of B or B bar. This is called as not of B. Not can be applied to a single variable only. So in circuit terms, what I will see is this is called as the not logic gate. This is B and this is B bar. This is called as a not logic gate. So if I want to draw the truth table, so let us say this is Y. If B is 0, we can take only two values 0 and 1. Then B bar will be the opposite, which is 1 and 0. So it is the most simple logic gate you will come across. It is the gate which essentially takes the reverse condition, or it essentially simply reverses what is the logic level. So in equation terms, I will say Y equals B bar, or if you have a single variable, I can say Y equals A bar. Right? So with this, we have seen essentially three kinds of logic functions. What is called as the AND, OR and NOT. For AND and OR, you need a minimum of two inputs or a minimum of two conditions. But for NOT, you can only have one input. And all of these gates have one output. So these AND, OR and NOT, they are called as the basic gates or basic logic gates. So AND and OR, you need minimum two inputs. And for NOT, it is only one input. But for all gates have one output. So therefore, let us very quickly see how to use these basic gates, or if some function is given in the form of an equation, how to represent them using some of these basic logic gates. So suppose I say example 1. I say Y equals A dot bracket B plus C. Now this AND operation is happening on B plus C. So as per the rule of simplification, you can simply look at the bracket first. Now there are three inputs A, B and C, as you can see, and one output Y. So what we can see is that B and C have to be odd first. This plus indicates OR. So therefore I will take B, I will take C, I will connect them by means of an OR gate. Now what is happening over here? I will get B plus C. Now this B plus C has to be ANDed with A because of the dot. So here we will get Y, this is A, this is B plus C, the two will be ANDed. This is how you can represent this very simple logic function. The second example we can take is, let's say Y equals A bar plus B dot C. So again we have three inputs A, B and C. Now what is happening inside the bracket? We have to do A bar plus B. So A has to be passed through a NOT gate to get A bar. First thing that we will do is use a NOT gate. If the input is A, the output will be A bar. And then we have to OR it with B. This is NOT, this is OR. So what do I have here? Input is A bar, here input is B. So it's A bar plus B. Finally, we have to AND it with C. So here it's y equals c dot a bar plus b, or a bar plus b dot c, whichever you want to say. So this is how to use basic logic gates to implement some kind of logic function. Now, let us use these basic gates that we have and go one step further. Suppose I take an AND logic gate and pass it through a NOT gate. So what essentially happens? I'm essentially having an AND gate over here that is passed through a NOT gate. So this is AND, this is NOT. So if my inputs are A and B, here it is A dot B. So here it will be whatever is the complement over here. This is called as A dot B whole bar. This function, which is NOT and AND, is called as NAND. Likewise, if I have an OR gate, again two inputs A and B, and then I have a NOT gate. Here the output will be A plus B, here the output will be A plus B, the whole bar. So NOT plus OR, this operation is called as a NOR operation. Now these essentially have equivalent representations. You take the AND, which looks like this, and take this circle or the bubble from the NOT gate and put it over here. This is called as a NAND gate, where the inputs are A and B, and the final output y is A dot B, the whole bar. Likewise, we can also represent something called as a NOR gate. You take the symbol of OR and the bubble from the NOT and put it over here. You have A and B, whose output is called as A plus B, the whole bar, and this is the NOR gate. This is called as the NOR gate. Now you might question why we are doing this. You might question why we are doing all this. What is the point of clubbing these two together? Well, there is a very important reason for this. But before we see the reason, let us try to write the truth table for these two gates. NAND, and we will also write the truth table of NOR gate. So I will say A, B and Y. Here also A, B and Y. Now remember that NAND is same as AND, except it is opposite of what it was. So if you recall, the truth table's output for the AND gate was 0, 0, 0, 1. So NAND will be just the opposite, which is 1, 1, 1 and 0. It should be 1, 1, 1 and 0. For OR gate, the output was 0, 1, 1, 1. So NOR will be the opposite, which is 1, 0, 0 and 0. So this is what the truth table of the NAND and NOR gates essentially look like. Now, back to the question that we were asking earlier. What is the purpose of the NAND and NOR gates? So, The use of NAND and NOR gates is tremendous. NAND and NOR are called as universal gates. They are called as universal gates. What this means is you can implement any logic function possible using only NAND gates or only NOR gates. You can implement any possible logic function using only NAND gates or only NOR gates. Only NAND gates or only NOR gates. So, with this statement, I am ending this particular lecture where we saw finally how we can represent analog voltages in digital form using a set of known voltages. And in particular, we saw how to represent them using ones and zeros, or what is called as the high and low voltage. Thereafter, we saw what are the basic logic functions, that is AND, OR and NOT. We saw their truth tables, we saw their gate symbols and the equations. Thereafter, we introduced what is called as NAND and NOR gates, which are essentially the complement of AND gates and OR gates respectively. And we are claiming that NAND and NOR are universal gates. That means we can implement any logic function using only NAND or only NOR gates. We are going to prove this in the upcoming lecture. Thank you.